Gravity is the force that holds galaxies together, keeps planets in orbit, and keeps you in your chair right now. You'd think we'd have a pretty solid handle on it by now. But here's the thing, when it comes to measuring gravity precisely, we're actually not that great at it. There's a number at the heart of all of this called the gravitational constant. Physicists call it Big G. It shows up in Newton's law of gravity and in Einstein's equations too. It basically tells you how strong the gravitational pull is between any two objects with mass. Without knowing Big G accurately, you can't fully calculate gravitational forces in a rigorous fundamental way. So what is it? The current accepted value is about 6.674 times 10 to the negative 11. The units are a mouthful, cubic meters per kilogram per second squared, but the number itself is what matters, and next to that number sits an uncertainty. A margin of error, and for a fundamental constant of the universe, that margin is surprisingly wide. We're talking about an uncertainty of roughly plus or minus 22 parts per million. That might sound small, but compare it to other constants. The speed of light is pinned down to essentially zero uncertainty. Planck's constant, which governs quantum mechanics, is nailed down to about 1 part per billion. Big G is off by a factor of thousands compared to those. Why is it so hard to measure? The short answer is that gravity is incredibly weak compared to every other fundamental force. Think about it. A small magnet can lift a paperclip against the entire gravitational pull of planet Earth. Gravity loses that contest easily. So when you're trying to measure the gravitational pull between two objects in a lab, the signal you're working with is tiny. And tiny signals mean tiny problems become huge headaches. The classic way to measure Big G goes back to Henry Cavendish in 1798. He hung two small balls from a thin wire, placed two large balls nearby, and watched the small balls twist toward the big ones. That twist told him how strong gravity was. It's elegant. It also has real limitations. The wire twists by an almost imperceptible amount. Any vibration, any air current, any tiny thermal change in the room can throw off the result. For over 2 centuries, physicists have tried variations of that same basic idea. And here's what's strange. Different labs using different methods keep getting slightly different answers. Not wildly different, but different enough that they don't fully agree. That's a red flag in physics. It suggests something is being missed. Maybe in the experimental setup, maybe in how the results are being analyzed, or maybe in ways we don't fully understand yet. That's exactly the problem a physicist named Stefan Schlaminger at the National Institute of Standards and Technology set out to tackle. He and his team spent about 10 years designing and running an experiment to measure Big G with a new level of care. 10 years is a long time, but this kind of work demands it. Their approach is built around a device called a torsion balance. It's in the same family as Cavendish's original setup, but far more sophisticated. The basic idea is still to watch how a hanging mass responds to the gravitational pull of nearby source masses. The difference is in how obsessively every possible error source is controlled and accounted for. The team used 2 different modes of measurement. In one mode, they let the balance swing freely and tracked its oscillation period, because nearby masses change how fast it swings. In the other mode, they used a feedback system to keep the balance still and measured how much force was needed to hold it in place. Running both methods on the same apparatus is powerful because each one has different sources of potential error. If both methods agree, you can have a lot more confidence in the result. The physical setup is also engineered to kill noise. The whole experiment sits on isolation systems to damp out vibrations. Temperature is controlled carefully because even small thermal changes cause parts to expand or contract. The source masses themselves are machined with extreme precision because if you don't know exactly where the mass is, you can't calculate the gravitational pull from it correctly. And then there's electrostatics. When objects get close to each other, they can build up small electric charges that create forces of their own. Those forces are tiny, but they're real, and they can masquerade as gravity if you're not careful. A huge part of precision work like this is identifying every non-gravitational force that could be influencing your measurement and then either eliminating it or modeling it well enough to subtract it out. After all that work, years of data collection, calibration, and analysis, the NIST team produced a new measurement of Big G. It's consistent with the current accepted value, which is reassuring. But the goal isn't just to confirm the old number, it's to tighten that uncertainty. Every time a well-designed experiment adds a new precise measurement to the mix, the global picture of Big G gets a little clearer. This matters beyond just having a more accurate number in a textbook. Big G sits at the foundation of gravitational physics. Better measurements help test our best theories of gravity. They matter for understanding the universe at cosmological scales. How galaxies cluster, how the universe expands, and they're relevant to practical systems like satellite navigation and geodesy, which is the science of measuring Earth's shape and gravitational field. There's also a deeper reason this work matters. When different labs measure the same constant and get different answers, that's science telling you something isn't fully understood. Chasing that disagreement is exactly how physics has made some of its biggest leaps. Maybe the discrepancies in big G measurements all come down to experimental imperfections that future work will resolve. Or maybe there's something more subtle going on with gravity itself at short ranges. Nobody knows yet. What's clear is that measuring something precisely, even something as familiar as gravity, is genuinely hard. It takes years. It takes carefully built equipment. It takes the patience to hunt down every tiny source of error. And sometimes, after all that, you still don't get the perfect, clean answer. You get a better one, and that's enough to keep going.